Dear students, welcome to our science episode. Today we are going to discuss light energy mirrors. Light energy mirrors. Did you see your picture in a mirror before? What happened? How does mirror work? Mirrors work by light reflection. So humans notice that when they look at the still surface of the water, they could see their image. And this also happens if they look at a shining, smooth surfaces like mirrors. This is due to light reflection. So this is the source of the light. These are the light rays, and they will hit the shiny surface and bounces back. This is called light reflection. So light reflection is when light bounces off when it hits a shiny, smooth surface. And this is what happens exactly with a mirror. This is called the law of reflection. We call the light rays that fall on a reflecting surface the incident ray. And we call the light ray that will bounce off the surface the reflected ray. So this one is the incident ray and this one is the reflected ray. The angle of incidence is the angle between the incident ray and a line perpendicular to the surface, and we call this red line the normal. And the angle of reflection is the angle between the normal and the reflected ray. The law of reflection states that the angle of incidence is equal to the angle of reflection. This is the first law. And the second law states that the incident light ray, the reflected light ray, and the normal line all lie in the same plane perpendicular to the reflecting surface. So the first law, the angle of incidence is equal to the angle of reflection. And the second law is that the incident ray, the reflected ray, and the normal all lies in a plane perpendicular to the reflecting surface. So give reason why the incident ray may reflect back on itself. How the incident ray will reflect back on itself. Of course, when the angle of incidence is equal to the angle of reflection equals 0. No angle of incidence and no angle of reflection. So that's why the reflected ray will reflect back on the incident ray. Predict the angle of reflection if the angle between the incident ray and the mirror is equal to 60. And we said, according to the reflection law, the first reflection law, the angle of incidence is equal to the angle of reflection. So here the angle is 90 because the normal is perpendicular to the surface. If he's giving you that the angle between the incident ray and the mirror is 60 degrees. So what is the angle of reflection? He wants this one. So it's 90 because this is from the normal to the mirror 90 minus 60. So this means that this angle is 30. The angle of incidence is 30. And hence the angle of incidence is equal to the angle of reflection. So also the angle of reflection will be 30. Types of mirrors. We have many types of mirrors. This is a plane mirror. The image, if you will look at a plane mirror, you will find your image upright and equal to the object. So the same, having the same size. The image is laterally inverted or reversed. So this means that your right hand will be opposite to your left hand, to the left hand of the image. And the image is a virtual image, so cannot be received on a screen. If you will hold writing like this, ABC or any other word, you will find it reversed on the mirror. So that's how the image is laterally inverted or reversed. The distance between the object and the mirror equal the distance between the image and the mirror. The same distance between the object and the mirror is the distance between the image and the mirror. And the straight line connecting the object and its image is perpendicular to the surface of the mirror. So can you give reason why the ambulance word is written inverted? Take a second to think about it. Why the ambulance word is written inverted on the ambulance car? Yes, in order for drivers to be able to read it correctly when they see it in the car mirror and evacuate the road. As I said, if you are having a plane mirror, so the image is laterally inverted. So for me to read the word ambulance right in the mirror, so it has to be written inverted. A boy stands in front of a plane mirror at 3 meters. Determine the distance between the boy picture and the mirror. The distance between the boy's picture and the mirror is equal to the distance between his body and the mirror. So it's the same, equals to 3 meters. What is the distance between the boy and his picture? So 3 plus 3, yes, 3 meters. The first 3 meters is between the boy and the mirror. And then the second 3 meters is between the mirror and the picture. So the total is 6 meters. The boy is away from his image by 6 meters. Determine the distance between the boy and his picture if he moves toward the mirror by 1 meter. So the distance between the boy and the mirror after movement is equal to 3 minus 1, equal 2 meters. So again, 2 meters from the boy till the mirror, and then again 2 meters from the mirror to the picture. The total will be 4 meters away. The second type of mirrors are spherical mirrors, and this is a sphere. It's like a ball. So spherical mirrors, it's when the mirror is apart from a sphere. Its reflecting surface is a part of a hollow sphere. Let's see together types of spherical mirrors. We have either concave mirrors, and they are converging, and convex mirrors, and they are diverging. This is a concave mirror. This is a concave mirror. The reflecting surface is a part of the inner surface of the sphere. So if this is a sphere, this is the inner part of the sphere. The reflecting surface is to the inside, and the rays will converge from the mirror. The opposite is the convex mirror, where the reflecting surface is to the outside. The outer is a part of the outer surface of the sphere, and the convex mirror are diverging. So the rays will diverge. Let's take some definitions. If this is a sphere and this is a convex mirror, where the reflecting surface is on the inner side of the sphere, what is the C? If we will draw a straight line and we will put this point, this C is the center of curvature, which is the center of the sphere, that the mirror is a part of it. In the convex mirror, the C, or the center of curvature, is in front of the reflecting surface. But here in the concave mirror, the center of curvature is behind the reflecting surface, because in concave mirrors, the reflecting surface is apart from the outside curvature of the sphere. The radius, or the R, the radius is half the distance of this line, and the pole of the mirror, which is the P, it's a point in the middle of the reflecting surface of the mirror. So whenever the reflecting surface is, the point in the middle of this reflecting surface is called the pole. So this is the pole of the convex mirror, and this is the pole of the concave mirror. While the principal axis, or the CP, this is the principal axis. This is the straight line that passes by the pole and the center of curvature of the sphere. Again, this is the principal axis. So what is a secondary axis? It's a straight line that passes by the center of curvature and any point on the surface of the sphere. Again, it is a straight line that passes through the center of curvature and any point on the surface of the sphere. Of course, except the pole, because if it is passing through the pole, it's called the principal axis. Well, the primary focus. The incident rays, look to this picture. These are the incident rays in green. They will fall on the reflecting surface of the mirror. Then the reflected rays will intersect in a point called the principal focus. This point lies on the principal axis. The distance between the principal focus and the pole, we will call it the focal length. So the distance between the focus and the pole is the focal length. And the focal length is half the radius of the sphere. So here is a question for you. The focal length of a concave mirror is 7 centimeters. Calculate its radius. We know that the radius is double the focal length. So if the focal length of a concave mirror is 7 centimeters, so the radius is 7 times 2 equal 14 centimeters. Now let's see the different images formed by concave mirrors. A concave mirror is known to be a converging mirror. So the incident ray that will come parallel, that will fall parallel to the principal axis on the reflecting surface, will reflect passing through the focus. So if the incident rays are parallel to the principal axis, the reflected rays will pass through the focus. And vice versa. If the incident rays will pass through the focus and fall on the mirror, the reflected rays will reflect parallel to the principal axis. So this means incident rays parallel to the principal axis, reflected rays will pass through the focus. Incident rays passing through the focus, so the reflected rays will be reflected parallel to the principal axis. What if the incident ray will pass through the center of curvature, the C point, and fall on the mirror? Therefore, the reflected light will pass also through the center of the curvature and reflects back on itself. Now, let's compare between the real image formed by concave mirrors and the virtual image. If the image is formed on a screen in front of the mirror, so here is the object, and here are the incident rays, and here are the reflected rays, the image is now real image formed by a concave mirror. The image is inverted and smaller in size. What about the virtual image? So the image that cannot be formed on a screen behind the mirror. So here is the object and here is the incident rays, and the reflected rays will form a virtual image that cannot be formed on the screen, and it's behind the mirror. It's not in front of the mirror, and the image is upright in position. So take a look at this table and let's define the object and then know the type of image that will be formed. So if the object is at a distance greater than the radius of the sphere. So the image will be between the focus and the center of curvature. The image is real in front of the mirror and inverted and smaller in size. What if the object is at the center of curvature, is at the point C? Then the object will also be formed at the center of curvature. It's real in front of the mirror, inverted, and equal in size to the object. What if the object is between the center of the curvature and the focus? Can you notice that when we come near the object, when it will come near, the image will go far from the mirror? So here, when the object will be between the focus and the center of curvature, so the image will be formed at a distance greater than the radius of the sphere, inverted and enlarged, larger in size than the object. What if the position of the object is between the focus and the pole? So it's very near to the mirror. Here are the incident rays. Here is the incident rays, and the image will be formed behind the mirror. So it's a virtual image, upright and magnified, and with a large size than the object. Where do we see concave mirrors? We can see concave mirrors in flashlights. We can see them in runways, in airports. We can see them in the front lights of the car, lighthouses, solar furnaces, and the shaving mirrors are also concave. Now let's discuss the image formed by convex mirrors. So a convex mirror is a diverging one. The incident light rays parallel to the principal axis will reflect, forming a virtual focal point behind the reflecting surface. So if it is convex mirror, if it is diverging one, so the incident rays parallel to the principal axis will reflect back, and their extension, the extension of these reflected rays, will form a virtual focal point behind the mirror. And the image is always virtual. The image is always virtual, smaller in size, upright and behind the mirror, even if the distance of the object is changed from the mirror. So at any distance from the mirror, the object formed by a convex mirror will be virtual behind the mirror in what we call a virtual focal point. And you can see convex mirrors at car side mirrors. Let's see this video about mirrors to understand how do they work.
Is going to hit the inside of here. We say this is the concave surface. So it's a concave surface. I remember this as though, like, if you're walking into the cave, it's concave. The other way, if the light was to hit on the outside, this we call convex. So concave, walking into the cave, the light is going to go into the cave. Convex, it's going to hit the outside. Okay, now the way the light behaves with a concave mirror is that it will actually focus into a specific point. So the light, you can see it there, it's traveling in straight lines. I've used the triple beam here just so we can see how it's behaving. So we've got 3 beams that are going to hit the mirror, and they're going to get reflected towards one another to create what we call a focal point or a focus. Okay, so you can see that point here. All right, see how all of those three beams, they all focus onto the same point after being reflected off that curved mirror. And we can move the curved mirror around, okay, but we still see a focus each time.
Dear students, thank you for watching and see you later in other episodes.